There are many situations in which we're concerned with the probability of more than one event at the same time. So we're not just going to want to talk about the probability of some simple or compound event happening, but we're going to want to think about multiple events and what if they occur at the same time, or what do they tell us about each other. So in order for us to do this, we need to actually introduce the concept of joint probabilities. So very often we'll be concerned with multiple events, and the joint probability is going to capture the probability that two or more events occurs simultaneously. So in order to define joint probabilities, we actually want to start by updating our definition using the term marginal probabilities. So the probability of a single event, which we just write as P of E, is sometimes called the marginal probability or the marginal probability of E. So when we have one event, we're referring to this as a marginal probability. Now this is going to be defined in contrast with the probability of multiple events occurring, which is referred to as the joint probability. So if we have two events, A and B, the probability that they both occur is the joint probability of A and B, and we're most often going to write it in this way right here, probability of A and B. So this would mean that both events A and events B happened at the same time. Now, note that the joint probability is actually just the probability of the intersection. If we're saying that both A and B happen, then we can write that as A intersect B. Right? So the joint probability is really just the probability of the intersection of A and B. Now, it's much more common for us to use this notation here for our joint probabilities, and so that's what we're going to start to do. But just know that the relationship is actually stemming from the intersection of two events. Now, joint probabilities are commutative in the sense that the probability of A and B is the same thing as the probability of B and A. So we can always switch the order, and oftentimes if we're writing down generic expressions, we'll just write them in sort of alphabetical or an ascending order, right? So the probability of A and B, okay? Now, if we had more than two events, we can extend out the notion of joint probability to as many events as we want. All right, so here we have a sequence of events, E1 up to EK. That's just defined to be the probability of the intersection of all of those, right? But ultimately, it's the same type of thing. Joint probabilities, we can have as many events as we would like. Now, events are generally combinations of outcomes, and so multiple events can occur at the same time, right? So we're not thinking about E as being all of these different outcomes, so it's possible that we have multiple events occurring at the same time. If we roll a die, you can get a number that is even, so being an even number could be an event, but you could also get a number that's less than 4, right? That's another event. Or you could get a number that is greater than 2. Right? So all of these are different events that might occur, and we can have all of these events occurring at the same time. And so when we're thinking about joint probabilities, we're specifically thinking about events that can occur at the same time. So suppose that we're rolling a single 6-sided die. What is the marginal probability that a 2 is rolled? Okay, so what's the probability that we get a 2? Now, it's not a trick question here, right? There are 6 possible outcomes. One of those is a 2, and so we know the probability has to be 1 out of 6. So we say the marginal probability of E1 is 1 out of 6. Now, what's the marginal probability that an even number is rolled? Now, again, we can go through, right? There are 2, 4, and 6, so we have 3 possible even numbers. There are 6 total numbers, so 3 out of 6, 1/2. Right? Half the numbers are even, half the numbers are odd. So the probability that we roll an even number is going to be 1/2. Right? And so what we have here is that the marginal probability of rolling an even number is equal to 1/2. Now, what's the joint probability of E1 and E2? Right? So what is the probability that both E1 and E2 happen at the same time? So here we need to roll an even number that is also a 2. Okay, well, a 2 is an even number, so that's totally fine. But there's no other numbers that are both 2s and even numbers, right? And so there's exactly one possible way that we can roll an even number that is a 2, and that's if we roll a 2. And so it's going to have to be 1 out of 6, right? And so the probability here is 1 out of 6. Now, if we want to compute joint probabilities generically, the specific information that we're given is going to have to dictate what our procedure for doing that is. So what we can do in some situations is we can use our rule for arbitrary unions. So the probability of the union of A and B is the probability of A plus the probability of B minus their intersection. Now, if we rearrange that, we actually get the probability for the joint probability, right? Because the intersection here, that's just our joint probability. And so we can bring that over to the other side. We swap it with the union, and we get this expression here. And so if you're given marginal probabilities of A and B, as well as the probability of the union of A and B, then that allows us to calculate the joint probability. So if the union's available, then the joint probability can be directly computed. Now, otherwise, it's often going to be easiest for us to actually just think about the intersection of A and B as a single event in itself, right? So we take some new event, which we'll call E, we define that to be A intersect B, and then suddenly our joint probability up here is actually just a marginal probability of E. And then we can use the same types of arguments we've used for marginal probabilities. So if all of the outcomes are equally likely, for instance, then what we can say is that the probability of A and B is going to be given by the size of the intersection over the size of our sample space, right? And that's because if we define E to be the A intersect B, then the probability of E, right, we just take A intersect B and we'll replace this with E here. It's going to be the size of E divided by S, and the size of E is exactly the size of that intersection, right? And so we can normally reason about this directly. So if we reason about the situation, we might be able to come up with the answer. Now, a very important thing to note here is that in general, the probability of A and B, the joint probability of A and B, is not going to be the product of the marginal probabilities. So that is to say, probability of A intersect B is not equal to the probability of A times the probability of B. This relationship does not hold in general. Sometimes it will, but it's not going to hold in general. This is often going to be memorized as a rule by students. This is presented falsely in certain places, and it's really important for us to know that this is not the rule. If you want joint probabilities, you cannot simply multiply them together. That is not going to work. And we'll see some examples of that as we move on. So consider an example here where we're putting 10 colored marbles into bags, and they all have numbers, right? They're numbered 1 through 10, and we see here in this table that the reds are numbered 1, 2, 4, and 6, the blues are numbered 3 and 5, and the greens are numbered 7, 8, 9, and 10. Okay, and so what's the probability that we draw a red marble? Okay, and so we can go through here and we can count up. Right? We know there are a total of 10 marbles, and there are 1, 2, 3, 4 red marbles, and as a result, we can say that the probability has to be 4 out of 10. Right? Of the 10 marbles, 4 are red, so it's 0.4 probability. Now, what's the probability that an even marble is drawn? And so for our even numbers, right, we have all of the even numbers between 1 and 10. So we have 2, 4, 6. We have 8 and 10. So there's a total of 5 even numbers represented there. There's a total of 10 numbers, and so 5 out of 10. The 10 marbles, 5 of them are even, so 0.5. Now, what's the probability that a red even marble is drawn? Okay, and so for here, we want the joint probability that it is red and that it is even. Now, notice if we go into our red marbles, there is a 2, a 4, and a 6. So there are 3 that satisfy both quantities here. If we think about A being the event that it's red and B being the event that it is even, then the set here is going to be 2, 4, 6. And so then the size of A intersect B is equal to 3. We know that the size of our sample space is equal to 10. And so then we go 3 out of 10. Okay, and so that will give us our answer here. Now, what we should note is that 3 out of 10 is not going to be the product of 0.4 times 0.5, right? So if we had taken the marginal probability from A, the marginal probability from B, we multiply them together, we do not get the correct answer here. And so again, important, we don't just multiply marginals to get our joint probabilities, we have to reason about the situation. Now, what's the probability that a green marble with a number less than 5 is drawn? And if we look at the green marbles, we have a 7, 8, 9, and 10. And so there are no green marbles that are less than 5. And so this probability has to be 0. Right? There are 0 marbles that satisfy this. Continue with this example here. Take R, B, and G to be the events that a red, blue, or green marble are drawn. What's the probability of R and B? What's the joint probability of R and B? What's the probability that we draw a marble that is red and blue? Now, there are no marbles that are both red and blue, and as a result, it has to be 0. What about the probability that we draw a marble that is red, or the probability that we draw a marble that is blue? Probability that we draw a marble that is red or blue, right? And so there's a couple ways that we can think about this, right? So we can first note the probability RUB is going to be the probability that we draw a red marble plus the probability that we draw a blue marble minus their joint probability that we draw a red and a blue, right? This one right here is going to be 0, which we just found in part E. And so it's just the probability that we draw red plus the probability that we draw blue. So that is going to be 4 reds plus 3 or 2 blues rather. And so then that's 6 out of 10. Okay. We could know this directly without having to write this term down if we remember our rule for additivity, right? The axiom of additivity. And the other way that you could reason through this is just by saying, well, we want to draw red or blue. And so if we just go through and we start counting up, we have 1, 2, 3, 4, 5, 6 marbles that are red or blue. Okay. And so there are 6 red or blue marbles, so 0.6. Alternatively, we could use the actual formula here. Now, what are the differences between the probabilities in E and F? Right? And so in E, what we're having is the probability that we draw a marble that is both red and blue. And in F, we have the probability that we draw a marble that is red or blue. Right? So the probability that the marble is red and blue is 0. The probability that the marble is red or blue is 0.6. Okay. And so again, we're differentiating ands and ors. We're differentiating intersections versus unions, and we're thinking about these in terms of our joint probabilities. What is the probability that an even red marble that is less than 5 is drawn? Okay, and so here, right, we have 3 events going on. We have the event that the marble is even, we have the event that the marble is red, and we have the event that the marble is less than 5. And so again, we can go through and we can just say, well, what marbles actually satisfy even red less than 5? Okay, well, 1 is not even, so that doesn't work. 2 and 4 are both fine, and 6 is not less than 5, so that doesn't work. And so there are 2 marbles that satisfy these traits, and so then we should have 2 out of 10. This is going to be the joint probability of E1, E2, and E3. There are 2 even red marbles less than 5, and so 0.2 is our probability. If we select 2 marbles, what is the probability that they are both red? Okay, and so again, here we can think about this in several different ways, right? But one thing that we could think about here is that we have a total of 4 red marbles, right? 1, 2, 3, and 4. We want to pick out 2 of them. We don't care about the order, so if that's 4, choose 2, gives us 6 ways of selecting our 2 red marbles. Then we'd have 10 total marbles, and we're going to pick out 2 of them, so there are 45 ways of selecting any 2 marbles. And thus, the probability that the first one is red and the second one is red is going to be 6 out of 45, which is the same thing as 2 out of 15. We could think about this as either a joint probability of the first one being red and the second one being red, or we could think about this as a marginal probability where we're drawing 2 and we're thinking about the event as being sort of paired observations here. Right? Either way, it's going to lead us to the same answer. Okay, now taking a look at a separate example now, we have students at a particular university, and of these students, 40% are known to take statistics, 25% take chemistry, and 50% are known to take at least one of statistics or chemistry. And the first part of the question is, what's the probability that a student takes both statistics and chemistry? And so we want the probability of statistics and chemistry. And what we know is that that can be written as the probability of statistics plus the probability of chemistry minus the probability of statistics or chemistry. Right? And so this is going to be 0.4 plus 0.25 minus 0.5. Right? And so that's going to give us our response for this first example here, because we're given directly the marginal and the union, the probability of the marginals and the probability of the union. And so if we plug that in, we get that 15% of students are taking both statistics and chemistry. Now, what's the probability that a student takes statistics but not chemistry? And so there's going to be 2 sort of major approaches that we could take here, right? So if we want statistics but not chemistry, then what we're looking for is statistics intersecting with the complement of chemistry. Okay, and so if we just draw out sort of a quick Venn diagram to sketch this, right? So this is all of our students here. We can put in our statistics circle and we can put in our chemistry circle. So that's statistics, that is our chemistry. So we want to be inside of statistics, right? Which is this whole circle here. However, we do not want to be in the chemistry circle. And so specifically, we're going to be anywhere inside of our statistics circle right here, but not in this area that is the joint area, right? And so in other words, if we take the probability that someone is in statistics, that is this whole circle here, right, including that joint area. And then if we subtract off the probability that someone is in both statistics and chemistry, right, then what we're doing is we're subtracting off this middle part here, right? We subtract off the part in between. And as a result, that's going to leave us with just the part of statistics that we're caring about, okay? And so if we take this sort of through our Venn diagram argument, then we can use that to calculate out this probability, okay? And so if we want the 40% of students take statistics, 15% of students take both statistics and chemistry, and so then 40% minus 15% gives us 25% of students taking statistics, but not chemistry. So the probability of S and C complement is the probability of S minus the probability of S and C, right? That's going to be true in general. However, we can also sort of think about this as coming sort of more directly from our intuition, right? Where what we're really thinking about here is the fact that every student in our campus here, of all of those students, right, 40% of them are in our statistics class, right? And we know that 15% of those of the students are in both statistics and chemistry. And so that 40% contains that 15%, right? It's considered in both. But what that means is that the rest of the 40% has to be students who did not take chemistry, right? And so we know that that is going to be the 40 minus the 15% gives us our 25%, right? And so we can reason through this sort of either by thinking about the scenario directly or by sketching this out with sort of our Venn diagram to come up with the rules. Okay? So joint probabilities broadly capture the probabilities of intersections of more than one event happening simultaneously. Marginal probabilities is the name that we give to probabilities of single events. And really the important thing to note here is that the lines between these are going to be quite blurry. There's not going to be a time where we can use strategies for marginal probabilities that aren't also going to be useful sometimes for joint probabilities, right? Because if we just think about the intersection as being a single event, then we can reason our way to the joint probabilities in much the same way. And so it's not always going to be clear cut. However, what we're going to see is that joint probabilities are going to be very useful for us for thinking about the information that we have, between sharing information between different events, and sort of using them in a broader context. And so marginal probabilities and joint probabilities, both very important. And the key distinction is, are we talking about one event or are we talking about more than one event?